Hi guys, my name is Arya, and today we are going to explore the realms of cybersecurity. With the advent of technology and the need for its security, the term cybersecurity has been coined into a singular word, but it is very evidently made up of two separate terms. Cyber, which refers to everything that comes under the digital culture, and security, which is the art of protecting or hiding an entity. So when you put the two terms together, it basically means the protection of everything that is digital. Well, that in itself makes it a very vast topic, including domains like application security, information security, cloud security. But due to time constraints, I'm going to be discussing one of the most important domains in my opinion, and that is network security. So before we jump in, let me tell you guys that this whole video will be actually divided into two parts. So the first part will be discussing about the network. And when we are discussing about the network, we're going to go through a packet structure, how packets are transferred from one computer to another, network architectures including TCP/IP model and OSI based models, and all the type of addressing like multicast, broadcast, and unicast. And we'll also be going over protocols like address resolution protocols and how they can be hacked. In the security aspect, we're going to be discussing firewalls and the types of firewalls and the two different flavors of cryptography, namely symmetric key cryptography and public key cryptography. And in the end, we are also going to perform a very interesting demonstration as to how to perform a man-in-the-middle attack and what a man-in-the-middle attack can do to your system. Okay, so let's begin with our session today. Okay, so first we're going through the network part and I'm going to teach you all how a network actually works. Okay, so I think it's right to assume all of you watching this video have downloaded some sort of file in the past. Whether it be a movie, a TV show, some software, or music, you have downloaded something off the internet, but most of you don't really know how the whole process works. Now let me take a moment to explain the whole thing. So first of all, when you click that juicy download button, your whole file doesn't really get sent to you all at once. Rather, it is broken down into tiny units called packets, which are then transmitted over a network to your computer. Now, the way how atoms make enormous objects together, data packets come together to form one big file. They can be considered the atom of a network, and like an atom, a data packet too has a pretty complex structure which can be broken down into three significant parts, namely the packet header, which generally contains critical information about where the packet is coming from and where it is headed, the payload, which is basically the data contained by the packet, and the packet trailer, which is just data to signify the end of a packet. Now, out of the three, the packet header is the most important to understand when understanding the structure of a network, so let's have a deeper look at it. Okay, now what you see on your screen at this moment is an IPv4 packet header. A little bit on IPv4 before we continue is that IPv4 is the fourth version of the internet and it is also the most widely used digital communication protocol. There's also IPv6, but it hasn't really been implemented widely. And about IPv5, well, let's say it's what Microsoft did with Windows 9. It doesn't exist. Now, it's pretty evident from what we look at that the IP header indeed is a complex structure with numerous parts. The IPv4 packet header consists of 20 bytes of data. An option part also exists within the header that allows further optional bytes to be added. But this is not normally used, with the occasional exception of something called a router alert. Now let's take a moment to discuss all the header files briefly. So first of all, we have the version part. Now this is always set to 4 in the current IP version, and it shows the version of the protocol that we are following. Next is the header length or the IP header length, and it's a number of 32-bit words forming the header, which is usually 5. Next is the DCSP field, which is for differentiated service code point. It is a 6-bit field, sometimes set to 0, but can indicate a particular treatment, sometimes reflecting the quality of service, needs of an applicant to the network, and the DCSP informs a router how to queue packets while they are waiting to be forwarded. Next is the ECN field, which stands for explicit congestion notification, and it tells us about the congestion in the network route. Next is this total length, which is the size of the datagram, and this is in bytes, and this is the combined length of the header and the data together. Next comes the identification field. Now, the identification field is a 16-bit number which, together with the source address, uniquely identifies a packet that is used during reassembly of a fragmented datagram. Next is the flags part. Now, there are a sequence of 3 flags. One of the 4 bits is unused and used to control whether the routers are allowed to fragment a packet and to indicate the parts of a packet to the receiver. Next is the fragmentation offset, and this is the byte count from the start of the original send packet sent by any router which performs IP router fragmentation. Next is time to live. Now, time to live is the number of hops or links which the packet may be routed over or decremented by most routers used to prevent accidental routing loops. It's a very important aspect of every packet. Next comes the protocol. Now, the protocol is the service access point or SAP, which indicates the type of transport packet being used and carried. For example, if it's 1, it's ICMP, if it's 2, it's IGMP, if it's 6, it's TCP, and if it's 17, it means it's following the UDP protocol. Next is the header checksum. Now, a once complement checksum is inserted by the sender and updated whenever the packet header is modified by a router, and it is used to detect processing errors introduced into the packet inside a router or bridge, where the packet is not protected by a link layer cyclic redundancy check. Now, packets with an invalid checksum are discarded by all nodes in an IP network. The checksum can be thought of something like a barcode. If the barcode gives you wrong information, you just discard that packet. Now, as you guys can see, the next field is the source IP address, and it is the IP address of the original sender of the packet. And next is the destination address, which is the destination field of the packet. And then we spoke about the options field. Now, it is not normally used, but when used, the IP header length will be greater than 5 32-bit words to indicate that the size of the option field has been included. Now, the Internet Protocol has been there for a long time, and there has been a couple of models that have really given the protocol a structure. The first model is called the OSI model, and the second TCP/IP. Now, both these protocols have a layered stack architecture, with each layer having very similar functionalities. First of all, let's have a look at the OSI model. Now, communications between machines is hard. Many details and considerations are important in order to relay some information from point A to point B, and therefore every system is left on its own and has a tendency to be very different. The OSI layer model was made as an effort to divide the process of communication into a number of steps, so every step could tackle some of the needed functions of the transmission separately. Now let me use a very strange analogy to explain all the functions of each of the layers in the OSI model. So suppose you want to send a number of objects, let's say a group of vases, to a friend of yours that lives on the other side of the world. He needs the said vases in order to put on some plants on a display. Now you and your friend represent layer 7, which is the application layer, which makes the final use of the sent object. Now you give this vase to another person, let's call him a professional packer. He takes your vases, puts it in several boxes, fills them with wrapping in order to prevent it from breaking, and closes the boxes completely. This professional packer represents layer 6, which is the presentation layer. Now this professional packer takes all the boxes, gives them to the guy and arranger. Now he doesn't know what is inside the boxes, but he knows they all go to the same friend of yours, so he labels them appropriately. So far, he represents layer 5, and that is the session layer. Now the arranger takes all the boxes down to an office who handles clients in dozens of other buildings. They keep in touch with hundreds of other agencies at the same time. They do not actually send the boxes, but they track them and know when a box for an order is missing, and so. These guys are layer 4, which is also called the transport layer. Now, one of the guys from the office actually takes all your boxes along with many others to a post office. This post office is the third layer. Here, it is given an address, the one of your friends, and this is the layer 3 that is called the network layer. Now, one of the guys from the post office takes all the boxes to a dock, and the guys at the dock pull all the boxes into a container. They know very little about what the boxes contain or where their final destination is. They only care about which other dock is this container headed to. Now this dock is representing layer 2, which is the data link layer. And finally, we have the ship. It only knows where it is headed and takes the container with it. It handles the waves, the conditions of the sea, the weather, and all the other physical conditions that none of the other layers have to deal with. The ship is layer number 1, which is the physical layer. Now, after all this, the ship gets to port, the containers are opened out here. Now, boxes which are meant for this address stay on the dock, and the others are put into other containers and another ship and sent on its own way. Now, all the staying boxes are sent to an associated post office, and layer 2 has done its job. Then the post office receives the boxes, maybe realizing some are missing. They call the sending post office to check what happened, and once they are sure all the boxes are there, they send it to the big office, and now layer 3 has done its job completely. Then the big office gets the boxes, checks they are all in the correct order and place, fill the relevant tracking data, and send them to your friend's arranger, and layer 4 has done its job completely. Then the arranger reads the label put by your arranger, and he makes sure everything is in order. He knows they are for your friend and calls the professional packer. Here, layer 5 has completed its job. Then the professional packer takes everything from the boxes, checks if everything is intact, and if everything is okay, he calls a friend and layer 6 has done its job. And finally, your friends get the vases, happily unaware of everything that happened on every layer. He sets up the plants on display and is happily continuing with his day. Now, this is how the OSI layer model has actually differentiated all the different steps that you need for one packet to reach from one computer to another. I hope that analogy helped you all understand how a packet actually travels from one computer to another. Okay, so it's time now that we discuss the TCP/IP model. TCP/IP specifies how data is exchanged over the internet by providing end-to-end communication that identifies how it should be broken into packets, addressed, transmitted, routed, and received at the destination IP. Now, TCP/IP requires a little central management, and it is designed to make networks reliable with the ability to recover automatically from failure of any device on the network. The advantage of TCP is that it is non-proprietary, and as a result, it is not controlled by any single company. Therefore, the Internet Protocol suite can be modified very easily. It is compatible with all the operating systems, so it can communicate with any other system on the network. And the Internet Protocol suite is also compatible with all types of computer hardware and network types. Now, the TCP/IP functionality is divided into 4 layers, each of which includes a specific protocol. The application layer provides applications with standardized data exchange. Its protocols include Hypertext Transfer Protocol, which is HTTP, File Transfer Protocol, which is FTP, Post Office Management Protocol, which is POP3, Simple Mail Transfer Protocol, SMTP, and Simple Networking Management Protocol, which is SNMP. Next is the transport layer. The transport layer is responsible for maintaining end-to-end communication across the network. TCP handles communication between hosts and provides flow control, multiplexing, and reliability. The transport protocols include TCP and the user datagram protocol, which is sometimes used instead of TCP for special purposes. Next, we have the network layer. Now, the network layer, also called the internet layer, deals with packets and connects independent networks to transport the packets across network boundaries. The network layer protocols are the Internet Protocol, which is the IP protocol, and the Internet Control Message Protocol, which is also abbreviated as ICMP. Last but not least, we have the physical layer. Now, the physical layer consists of protocols that operate only on a link. That is the network components that interconnects nodes or hosts in the network. The protocols in this layer include Ethernet for local area networks and Address Resolution Protocol. So now that we've discussed the models which describe the architecture, let's move on to the different ways packets can be addressed to other devices. Majorly 3 main ways of addressing, namely unicast, broadcast, and multicast. Now, unicast is a term used to describe communication where a piece of information is sent from one point to another. In this case, there is just one sender and one receiver. Unicast transmission, in which a packet is sent from a single source to a specified destination, is still the predominant form of transmission on local area networks within the Internet. All local area networks, example the Ethernet and IP networks, support the unicast transfer mode, and most users are familiar with the standard unicast applications. Example HTTP, SMTP, FTP, and Telnet, which employ the TCP transport protocol. The second type of transmission is broadcast. Now, broadcast is the term used to describe communication where a piece of information is sent from one point to all other points. In this case, there is just one sender, but the information is sent to all connected receivers. Now, broadcast transmission is supported on most LANs and may be used to send some messages to all computers on the LAN. Example, the Address Resolution Protocol uses this to send an address resolution query to all computers on a LAN. Now, network layer protocols such as IPv4 also support a form of broadcast that allows the same packet to be sent to every system in a logical network. Last but not the least is multicast. Now, multicast is a term used to describe communication where a piece of information is sent from one or more points to a set of other points. In this case, there may be one or more senders, and the information is distributed to a set of receivers. One example of an application which may use multicast is a video server sending out network TV channels. Simultaneously, delivery of high-quality video to each of large numbers of delivery platforms will exhaust the capability of even a high-bandwidth network with a powerful video clip server. This poses a major scalability issue for applications which require sustained high bandwidth. One way to significantly ease scaling to larger groups of clients is to employ multicast networks. Now, unlike broadcast transmission, multicast clients receive a stream of packets only if they have previously elected to do so. Membership of a group is dynamic and controlled by receivers, And the router in a multicast network learned which subnetworks have active clients for each multicast group and attempts to minimize the transmission of packets across parts of the network for which there are no active clients. Okay, so let's see. We've discussed the various types of addressing, the fundamental unit of a network, and the network architecture that are widely followed. Now let's see how connection is actually established when you actually make a request. So suppose you're on a browser and you type www.google.com and hit enter. Now when you hit enter, a series of transactions takes place. Firstly, a packet called a SYN packet is sent from your computer all the way across the network to the IP address of the Google server. We'll get to IP addresses in just a bit. Now when Google server receives the SYN packet, it realizes that we are trying to establish a connection with Google, so Google sends back a SYN-ACK packet, which stands for acknowledgement. This is basically a way to say, hey, I acknowledge the fact that you're trying to connect to me. Now this ACK packet is sent to our computer all across the network. Finally, when our client computer receives the SYN-ACK packet, it sends back another packet called the ACK packet, which basically is an acknowledgement of an acknowledgement. Now after the SYN-ACK packet is received by Google, a connection is set up between your computer and the Google server. This process is the famous three-way handshake. Now in TCP, basically every packet comes with an ACK packet to say, yep, I got it. And if you don't get an ACK, you resend it. Now since this is a two-way communication, you want to make sure that your desire to connect got through to the receiving computer, and thus they send back the SYN-ACK packet. And they want to know that whether you got their acknowledgement or not. So you send back the acknowledgement of an acknowledgement, which is basically the ACK packet. Now both parties have positive confirmation that the other party has received and agreed to their request to connect. Now a good question might have arisen in some of your minds that how does one know who is what on a network? Well, that is solved by the computer's address, which is basically divided into two addresses, one the physical address, which is the MAC address, and one the digital address, which is the IP address. An IP address, also short for Internet Protocol Address, is an identifying number for a piece of network hardware. Having an IP address allows a device to communicate with other devices over an IP-based network like the Internet. Now, most IP addresses look something like four numbers that are divided by three dots. For example, 151.101.65.121. That's probably valid IP address. Now, if I'm going to send a packet to my friend in another country, I have to know the exact destination. It's not enough just to put a package with his name on it through the mail and expect it to reach him. I must instead attach a specific address to it, which you could do by looking it up in a phone book. This is exactly what the IP address is. You can generally find your own IP address by typing in ipconfig on Windows system or ifconfig on a Linux-based system. Now moving on to MAC addresses. Well, in a local area network or other networks, the MAC address is your computer's unique hardware number. When you're connected to the internet from your computer, a correspondence table relates your IP address to your computer's physical address or MAC address. The MAC address is used by the media access control sublayer of the data link layer of telecommunication protocols. There is a different MAC sublayer for each physical device type. The other sublayered levels in the DLC layer is the logical link control sublayer. Now, if you have access to the internet from a local area network in your home or business, it is possible that you share an IP address with some other user. This is because while you might use a different computer or device, you all use the same internet connection or the same access gateway. Now, in the early days of the internet, people connected to their modem directly to their computer. After all, most homes only had one computer. Today, most homes contain several devices that connect to the internet. Therefore, it is far more common to connect a DSL or cable modem to a router that can be accessed by multiple devices. Now, some modems even include a built-in wireless router. Now, your router gives each connected device a unique internal IP address that distinguishes differently on different local networks. This address are automatically distributed by the router using a protocol called DCHP. Typically, IP addresses of local devices might be 10.1.1 or 10.0.1.3, and some routers may also use the IP address that use the whole 192.168.x.x format. But this is not true for MAC addresses. Every device on this planet has a unique MAC address. MAC or Media Access Control Address is a globally unique identifier assigned to a network device, and therefore it is often referred to as a hardware or physical address. MAC addresses are of 6 bytes. The first 3 bytes are ID numbers of the manufacturer, which is assigned by an Internet Standards body, and the second 3 bytes are serial numbers assigned by the manufacturer itself. Okay, so that was about MAC addresses and IP addresses. Now, what happens when you're actually trying to connect to some other computer on a local area network? So when you're on a local area network, a certain protocol called ARP, which stands for Address Resolution Protocol, is used to communicate with other devices on the network. The term address resolution refers to the process of finding an address of a computer in a network. Now, the address is resolved using a protocol in which a piece of information is sent by a client process executing on the local computer to a server process executing on a remote computer. The information received by the server allows the server to uniquely identify the network system for which the address was required and therefore provide the required address. The address resolution procedure is completed when the client receives a response from the server containing the required address. Now, if you realized, ARP isn't really using a three-way handshake mechanism or any authentication, so this can be very easily exploited. All you have to do is lie when someone sends an ARP request. Now, you could lie to a computer that you are the router, and you could lie to the router that you are the victim computer. This is what we call ARP spoofing, and an attack like this is called a man-in-the-middle attack. An MITM attack happens when a communication between two systems is intercepted by an outside entity. This can happen in any form of online communication, such as email, social media, web surfing, etc. Not only are they trying to eavesdrop on your private conversation, they can also target all the information inside your device. Now, taking away all the technicalities, the concept of an MITM attack can be described in a simple scenario. Now, imagine being brought back to the days when old snail mail was being actually used. Jerry writes a letter to Jackie expressing his love for her after years of hiding his feelings. He sends the letter to the post office and it is picked up by a noisy mailman. He opened it and just for the hell of it, he decided to rewrite the letter before delivering the mail to Jackie. This results in Jackie hating Jerry for the rest of her life after Jerry called her a fat cow on the letter. The moral of the story is the mailman is a jerk, and so are all the hackers that do the same. This is exactly where the security aspect of network security comes into play to protect our data from unauthorized access, unauthorized modification, and unauthorized deletion. And the most common type of security measure that every computer uses is a firewall. A firewall is a software or firmware that enforces a set of rules about what data packet will be allowed to enter or leave a network. Firewalls are incorporated into a wide variety of network devices to filter traffic and lower the risk that malicious packets traveling over the public internet can impact the security of a private network. Now, firewalls, while they come pre-installed, can also be purchased as standalone software applications. Now, generally speaking, there are three types of firewalls: packet filtering firewalls, application or proxy firewalls, and hybrid firewalls. Let's look at packet filtering firewalls first. Now, packet filtering firewall just check the packet header of packets that are being sent to your computer. They analyze the packets according to rules written in a file called ACL, which stands for Access Control List. Packet filtering firewalls are already installed in your router and provide the cheapest form of security, but it is underwhelming as a payload is not checked. So basically, it checks the packet header, but not the payload, so it's not a very good type of firewall. But it always comes pre-installed in a computer. Next up is application firewalls, which are completely different from packet filtering firewalls. They check both the payload and the packet header. And above that, proxy firewalls have their own IP address, so when you access the internet through the proxy firewall, you're actually hiding yourself from malicious users by masking your IP with your firewall's IP. This is the basic principles on how proxy servers and proxy firewalls work. Last but not the least is a hybrid firewall, which is the combination of application firewall and a packet filtering firewall. They provide much higher security, but it should be noted that they must be applied in series. When they're applied in parallel, the security is brought down to the level of a packet filtering firewall, and the networks act like the proxy firewall doesn't exist at all. Now, that was all about firewalls. But in all honesty, it is comparatively much easier to break a firewall than modern encryption systems which are used to protect data. So when talking about encryption, we are talking about cryptography. Now, cryptography comes in two flavors, namely symmetric cryptography and public key cryptography. So first, let's discuss symmetric key cryptography. Now, an encryption system in which the sender and receiver of a message share a single common key that is used to encrypt and decrypt a message is called symmetric key cryptography. Now, this contrasts with public key cryptography, which utilizes two keys, a public key to encrypt a message and a private key to decrypt them. Secret key systems are simpler and faster, but their main drawback is that two parties must somehow exchange the keys in a secure way. Public key encryption avoids this problem because the public key can be distributed in a non-secure way, and the private key is never transmitted. Now, symmetric key cryptography is sometimes also called secret key cryptography because the security of this whole encryption algorithm depends on how secret you can keep your key. Now, cryptographic key is the core part of a cryptographic operation. Many cryptographic systems include a pair of operations such as encryption and decryption, and a key is a part of the variable data that is provided as an input to cryptographic algorithms to execute this sort of operation. Now, in a normal symmetric key cryptography, you'd probably have a plain text. Suppose the plain text, which is the quick brown fox jumps over the lazy dog, which is put into an encryption algorithm which contains the key and the message, and you get a ciphertext. Now, the ciphertext is then also put into a decryption algorithm which uses the same key, and then you get the plain text that produced the ciphertext. This is how simple symmetric key cryptography works. Now, in public key encryption systems, any person can encrypt a message using a receiver's public key. That encrypted message can only be decrypted with the receiver's private key. So, to be practical, the generation of a public and private key pair must be computationally economical. Now, the strength of a public key cryptographic system relies on computational effort or the work factor in cryptography that is required to find the private key from its pair's public key. So effectively, security only requires keeping the private key private, and the public key can be distributed without compromising security. Public key cryptography systems often rely on cryptographic algorithms based on mathematical problems, particularly those inherent in certain integer factorization, discrete logarithms, and elliptic curve relationships. Public key algorithms, unlike symmetric key algorithms, do not require a secure channel for initial exchange of one or more secret keys between the two parties. So because of the computational complexity of asymmetric encryption, it is usually used only for small blocks of data, typically the transfer of a symmetric key encryption system. This symmetric key is then used to encrypt the rest of the potentially long message sequence, and the symmetric key encryption and decryption is based on a simpler algorithm that works much faster. So because of the computational complexity of asymmetric encryption, it is usually used only for small blocks of data, typically the transfer of a symmetric encryption key. Example is session key. Now this symmetric key is then used to encrypt the rest of the potentially long message sequence, and the symmetric encryption and decryption is based on simpler algorithms that is much faster. Okay, so now it's time for an interesting demo on why you actually should really be aware of cybersecurity. So for this demonstration, I'm going to be showing you guys a man-in-the-middle attack. So for the man-in-the-middle attack, as we earlier discussed, we are going to need to ARP spoof ourselves to another computer and ARP spoof ourselves to the router too. So that means we are going to fool the computer that we are the router, and then we're going to fool the router that we are the computer. So for this demo, I'm going to be using two machines. One is going to be running Linux, and on the Linux-based machine, I'm going to be performing the attack. And for the victim, I've chosen it to be my own machine. And for the results, you guys will see how I'm going to sniff out all the images that is being served on the victim machine. So for this demonstration, we are going to be using a framework called Websploit. Now, Websploit is an open source framework and it's easily available on Linux, and it can help simulate man-in-the-middle attacks just for educational purposes. So let's get started. So first of all, we are going to start up Websploit by typing in the command Websploit. So once you go into Websploit, you go show modules. So as you guys can see, we have so many modules available out here. And these are all the types of attacks that you could possibly simulate with this framework. So we're going to choose the man-in-the-middle attack. So that is, we're going to use network/MITM. So now out here, you're going to see all the options that we're having. So as you guys can see out here, the Websploit framework gives us numerous amounts of options to set up. First, we can set the interface that we're going to attack on, and then we can also set the router that we're going to attack through. Then we can set the target IP address, and we can also set from a number of different sniffers. For example, we can use DriftNet for sniffing out victim images. We can use URL snarf for sniffing out victim links. Then we can use dsniff for sniffing out all sorts of passwords. Also, we are going to use SSL strip for actually stripping down SSL protocols so that you're not actually visiting a secure site. So firstly, we need the IP address of our victim's computer. So I'm going to go on my computer and check out my password. So ipconfig. So as you guys can see, my password out here is 192.168.2.142, and my default gateway is 192.168.1.1. So that means my computer, this is .2.142, is connecting to the router, which is then connecting to the rest of the internet through 192.168.1.1. So To check out my attacking computer's IP address, we're going to go ifconfig, and we see that we're running on the interface WLP2SO. You can also check that by going route-n, and this will show you the gateway that it's 192.168.1.1 out here, as you guys can see. And our IP address is out here, 192.168.1.215. So this is our attacking IP address. So moving on to Websploit now. Okay, so first we need to set our interface. So we go set interface. So that sets our interface. Then we need to set the target, as the router IP address is already correct. So our target is going to be 192.168.2.142, 192.168.2.142. And we're going to use the DriftNet sniffer for sniffing out all the victim images. And SSL is true, so let's just check we've got everything correctly. Show options. So yes, our interface has been set, our router has been set, the target has been set, we've set our sniffer, and SSL stripping is on. So all we have to do now is run our attack. So first we're going to forward all the IP. Now we're going to ARP spoof it. That's going to just lie on the network that we're somebody else. So now that we've run the attack on our attacking computer, it's time we go and browse some images on Google. So let's look at some images of Lamborghinis. So let's search for Lamborghini. So as you guys can see, it'll sniffing out all the images of all the Lamborghinis that I'm looking at out here. Like this Lamborghini looks really cool. This crashed one. There's so many Lamborghinis to look at. So as you guys can see, whatever images that you're looking at is just being sniffed out of the network, and I can see them as well as an attacker. So this gives you a measure of the magnitude of information that can be stolen from you just through a simple man-in-the-middle attack that can be actually performed with regular softwares that are available for open source use. Okay, so that was it for our demo. That was all about cybersecurity for today. I hope you guys enjoyed this session, and I hope you guys enjoyed the demo too, as it showed how much a hacker can steal from you. And I hope you guys learned something today. That's it from me. Goodbye.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!